So, welcome to RF transceiver design course. We are discussing stability and amplifier design. In the last class, we have discussed about the various power gain equation and we have derived the power gain equation by using a signal flow graph. Now, we will try to design the amplifier using those equation. So, when we try to design as discussed in the last class, our design target is to find the gamma s and gamma l at the given frequency, and we if we want to maximize the gain GT, or if we want to go with the specific gain GT which is less than GT max. And while designing we also need to discuss the how if you want to go for a minimum noise or maximum output power, and how can we obtain the maximum gain. So, what is the preliminary answer to the maximum gain? So, this is the input reflection coefficient gamma in, that is output reflection coefficient gamma out, this is gamma s and gamma l. So, in order to get the maximum transducer gain GT occurs when you have a ZS which is Z in conjugate. So, this ZS which is this at this node there is a conjugate matching, so that we will have a maximum power transfer. That means you have a gamma s which is a gamma in conjugate. Similarly, you will have a ZL which is Z out conjugate at this node, and gamma L which is equal to gamma out conjugate. So, assuming, so this is very important, assuming the device is stable for the gamma S and gamma L that you have selected. Otherwise, if your this ZS or ZL what you have choose, it is lying in the unstable region, then you cannot achieve the maximum gain. So, this is very important condition that we have assumed here, that your gamma S and gamma L is lying in the stable region. So, what are the attributes of power gain? Which power gain you should use for getting the maximum gain? So, GT is the ultimate gain figure of merit that matters, but we will find that GT is easy to use with unilateral device. We already discussed in the last class what is a unilateral device, where S12 is equal to 0. But it is very challenging for bilateral device where S12 is not equal to 0. So, when we have a S12 is equal to 0, that is a unilateral case, we can easily use a GT equation. So, for bilateral transistors, we shall start the design of the amplifier using either GA or GP equation and make this power gain equal to GT by appropriate matching. So, how you can do the because all the formulas are interrelated. If you make a GT where gamma S is equal to gamma in conjugate, it is a function of gamma L, it is nothing but GP gamma L. Similarly, GT gamma S where gamma L which is output conjugate match, GA is a function of gamma S. So, GT you can represent in terms of GP and GA. So, and another things to note that GT max or GA max is equal to GP max. So, this is always true, that if you have any maximum gain, either if you consider a GT or GA or GP, all are equal. So, if you want to go for a maximum gain for unilateral case, when you have S12 is equal to 0, there is a no feedback, means your output and input are not related, means your output signal from output to input it will not flow, that is a S12 is equal to 0, and that the device is stable if S11 is less than 1 and S22 is less than 1, because then your gamma in is directly function of S11 and gamma out is directly function of S22. So, that is gamma in is equal to S11, because you have considered S12 is equal to 0, gamma out is equal to S22. So, you can directly write in GT formula S11 gamma S square, S22 gamma L square. So, becomes the unilateral transducer power gain at the source side, because this will provide the gain at the mismatch gain at the source side, that will be mentioned as a GS. This is a defined for 50 ohm, that is for transistor gain S21 square, that is a G naught, and this is a mismatch gain at the load side, that is a GL. So here GS and GL can be larger than 1. So this GS and GL, and S21 which is a GT for ZS equal to ZL equal to 50. So might not be the optimal termination. So here to get the maximum unilateral gain GTU max, you should match gamma S with the S11 conjugate and gamma L which is a S22 conjugate. So then you can directly write 1 by GTU max is equal to 1 by 1 plus S11 square into S21 square 1 by 1 plus S22 square. So this is nothing but a S source mismatch gain at the source side is maximum gain is GS max, where gamma S is equal to S11 conjugate, and maximum gain at the load side where gamma L which is equal to S22 conjugate. Where when you can when you write the same equation GTU max and consider the k, that is S11 square minus S22 square plus delta square by 2 into S12 S21, and this is a delta, you can write GTU max in terms of the stability parameter k as well. And what is the requirement for to get the k stability? It is a k greater than equal to 1. So here in this case, if you want to get the maximum stable gain, and if you consider k is equal to 1, then the maximum stable gain you can get, that is a S21 by S12. But in this case your gamma S is matched with the S11 conjugate and gamma L is matched with the S22 conjugate. So this is a maximum equation for the maximum stable gain. So this is a GTU max, same thing you can also get GTU or GA or GP max, all are equal. Now there is a bilateral case. In the bilateral case, your S12 is not equal to 0. So here you already have a gamma in, we are multiple time we have used this equation, and this is a gamma out. So maximum transducer power gain GT occurs when ZS is equal to Z in star or ZL is equal to Z out star, or gamma S is equal to gamma in and gamma L is equal to gamma out conjugate. So you can directly write this gamma L conjugate, because gamma in or so gamma out is equal to gamma L. So you can write gamma L conjugate, which is S22 plus S22 S21 gamma S by 1 minus S11 gamma S, and gamma S conjugate which is applied to gamma in. So S11 plus S12 S21 gamma L by 1 minus S22 gamma L. So if we try to find out the equation, so here gamma S you can take, that is gamma L on this side. You can write this equation, that is gamma S S11 conjugate, and this will come into the denominator into S22 square, where gamma L is equal to S22 minus delta gamma S by 1 minus S11 gamma S. Again you try to put this gamma L in this equation, then you will have a function in the form of a gamma S. So because we are interested to find out the value of gamma S, so this is a gamma S 1 minus S22 square plus gamma S delta S22 star minus S11 equal to this complete equation that will come. So using the result that delta and S11 S22 conjugate minus S12 S22 conjugate allows this to be rewritten as a quadratic equation for gamma S. So we can find out the value of gamma S by using this quadratic equation. So it is nothing but a x square plus bx plus c. So there a is this, b is this, and c is equal to this equal to 0. So this is a quadratic equation, and we all know the solution of ax square plus bx plus c, we can find out the value of gamma s. So, there is a two values that you will get, plus or minus b1 plus or minus b1 square minus 4 c1 square by 2 c1. So, this is here, let us say this is a b1. So, in the next it is considered b1, and this is a c1 divided by 2 c1. Similarly, you can also get also get the solution for gamma l, that is b1 plus or minus b2 square minus b2 plus or minus b2 square minus 4 c2 by 2 c2, and where b1 and b2 is given by b1 b2 and c1 c2 is given by this equation. In this case, solutions are only possible if the quantity within the square root is positive. So, this both should be positive, and what it says that it can be shown that this is equivalent to k greater than 1. So, if you have a stable, means if your condition of stability is proved, that is k greater than 1, then always this should be the greater than 1. So, it is a direct relation with the stability of your amplifier. So, once you have find out this, you will get gamma s and gamma l. So, in this case, so in the previous case, we have directly considered gamma s is equal to S11 conjugate and gamma l is equal to S22 conjugate, but that was a unilateral case, and here this is a bilateral case. So, in the bilateral case, you cannot ignore S12. So, S12 is not equal to 0. So, always keep in this mind, this equation is valid for a bilateral, and it can be used for unilateral also, but when you have a unilateral, you should use a S12 is equal to 0. So, let us take one example, so that everything will be clear to all of you. So, design an amplifier for maximum gain of 4 gigahertz. You can use a single stub matching. So, stub matching also can be used, or you can use a LC matching that we have discussed in the while discussing the impedance matching. So, you can either use the single stub matching or the LC matching. Calculate and plot the input return loss and the gain from 3 to 5 gigahertz. The transistor is a gallium arsenide MOSFET. So, this is a foundry has provided the gallium arsenide MOSFET, and for different biasing condition, the S parameter can be find out. These are the S parameter at a different frequency. So, S parameter is given by the foundry based on the biasing, that is at 3 gigahertz, at 4 gigahertz and at 5 gigahertz. So, at 3 gigahertz this is the S parameter, at 4 gigahertz these are the S parameter, and 5 gigahertz these are the S parameter. So, if you want to design the amplifier at microwave frequency, you should you should know the S parameter prior to the doing the design. So, you can either use a simulator. So, simulator will also provide you S parameter, and you can also get the if you are using a specific transistor like gas or GaN, you will get from the foundry. So, what are the steps involved here? First is find the stability condition. So, you need to find out the stability. Second is find the value of gamma S and gamma L. Then find the gain and design the matching network. So, these are the important steps. If you follow this step for all the design, you can design any amplifier that you want. So, first is a stability. So, for stability you can use the K delta test. So, for f which is equal to frequency which is 3 gigahertz, K is less than 1 and delta is also less than 1. So, this is unstable for frequency of 3 gigahertz. For frequency of 4 and 5 gigahertz, k is greater than 1 and delta is also less than 1. So, this for these two frequency you can design and it is a stable. So, you can write a gamma s formula for gamma s and gamma l. You will get the gamma s, that is by putting all the values you need to find the B1 C1 based on the equation that we have discussed. It is based this B1 B2 C1 C2 are directly related to the as it is directly related to the S parameter. So, delta A has also related to the S parameter and B1 B2 C1 C2 you can easily find out. Once you have find out the value of gamma S and gamma L, by using that gamma S and gamma L value, you can put in the GS, which is equal to 1 by 1 minus gamma S square, which is equal to 4.14, that is 6.20 dB. Then there is a G naught, that is equal to S21 square, that is a 6.76, you will get the 8.3 dB. And GL again you can write that is 1 by 1 minus gamma L square. So, here you will get a 2.22 dB. So, your GT max is given by GS plus G naught plus GL, which is equal to 16.7 dB. So, this is the maximum gain you will get GT max, and here why we have considered gamma S and gamma L this equation, because if you see the S parameter, your S12 is not directly 0. So, before going to use any equation you should make sure that your transistor is a unilateral or bilateral. So, here it is a bilateral because your S12 is not equal to 0, and that is why we have used this equation gamma S and gamma L. Once you have find out the value of gamma S, you can find out the maximum gain, because what is the question here, we need to calculate and plot the input return loss and the gain from 3 to 5 gigahertz, and we want to design an amplifier for maximum gain at 4 gigahertz. So, this is a design criteria, we want to go for the maximum gain. So, that is a GT max, you will get a 16.7 dB. Make sure that you should have this gamma S value and this is a gamma L value. So, once you have a gamma S or gamma L, you can use a stub matching, or you can also use a matching LC matching. So, LC matching can also be used or stub matching can also be used. So, in stub matching what you will do is you will use a transmission line in order to do the matching. So, how the stub matching work? If you have certain ZL that you want to match, and there are two kind of stubs. So, what here there is a open and short circuit stub. So, this is a short circuit stub. So, first you need to find the distance D and length of the stub L. It can also be mentioned in terms of a transmission line also, means in terms of microstrip line also you can represent. So, this distance L, first you need to locate the value of gamma S here, and then once you have located the value of gamma S, first because it is a, what is a stub? If it is a open circuit, you should use from this line. If it is a short circuit, you should use from this line, because right side is a open circuit and left side is a short circuit. So, how you can find out? First you just take a 180 degree phase shift, because here Z we are converting to the Y. So, once you have converted to the 180-degree phase shift, this is a point. Now, from this point what you want is a length of open circuit stub. So, you should, because you have converted to the Y, you are going to take the uh, this point, because this if you consider the Y Smith chart, the on this side the short will be open, then from this to this will provide you the length of the open circuit stub. So, what you want is a Ys should be match. So, here you will get a Ys, and then there is another point here, that is that at that point you will get a 1 plus Jb, and that Jb you should, because you will get a 1 plus Jb here, that Jb if you want to cancel, this stub should provide the minus Jb. So, that minus Jb you will get by from when you put a minus J here, minus Jb, and you can find out the length of stub. So, this is the way you can also do the stub matching. You can also do the LC matching. LC matching we already discussed. If the point is here, you can move down or up by using the ZY Smith chart. So, if you try to plot, this is a length 0.120 lambda, and this is a 0.206 lambda. So, this is a stub, that is we have done the matching. So, this at the input side and output side by using the gamma s, because this will always be the 50 ohm, and then you have a gamma s here and the gamma L, you can find out the impedance matching, and if you do the impedance matching you can plot the GT, that is the gain curve, and the return loss, that is more than 20 dB at the desired frequency of 4 gigahertz, and you will get the maximum gain. What is the maximum gain? That is a 16.7 dB. So, this is the way you can design the amplifier. So, what is the method, complete method to design amplifier is, first you should know the stability. So, we have discussed the stability curve and how you can plot the stability circles, input stability circle and output stability circle by using the S parameter. Once you have find out the stability gamma s and gamma L, if you have made the transistor unconditionally stable by using some resistive network, or you can choose a value of gamma s at in the stable region, either gamma s or gamma L in the stable region. If your k delta, you can also use the k delta or the mu test in order to find the stability. Once you find out the stability, you can go for the gain. So, if you are targeting the maximum gain, you can find the value of gamma s and gamma L according to the, if it is a unilateral case or a bilateral case, and based on that equation of unilateral and bilateral, we will get a GT max, and once you got the gamma s and gamma L value for the maximum gain, you can find the input impedance and output impedance matching network. So, this is a final circuit where the biasing is not shown. You need to bias this transistor in order to get the S parameter. Thank you.